locally like this. So for example, like some part of the cylinder where you just take like the upper part without the vortex. That would be a nice surface. So so the ruled surfaces are depending on like the parameters you choose are sometimes nicely in our definition and sometimes not. So maybe as a warning. Depending on what kind of like curves I choose, I might end like up with some surface that is nice, like, and sometimes I end up with something that is not nice. So just like be careful that not everything that is called a surface is actually a surface in our definition, and that's like something to keep in mind there. Okay, but that brings us like to the question of how do we actually construct surfaces? How do we, if I give you a certain object and say to you, is that object a surface? For example, is the cylinder now a surface or not? So you can think of that like, yeah, maybe I think of like, okay, I can like cover that half with a certain coordinate chart, and then I cover like this part with a coordinate chart, and you can like talk about that. But that's actually, depending on the applications, it might be relatively hard to do that. As we have seen, for example, with the sphere, we need like 5 or 6 coordinate charts, and it's like a bit tricky to talk about that. So I want to give you some tools to like make your life easier. If you have like some homework exercises where I say like, please show that this and this is a surface, you have like some a bit more like refined tools than just going back to the definitions and constructing charts by hand. So let's see how we can go. There are essentially two ways how to construct a surface, or to say when a given subset is like a surface. And the first one is using graphs. So for example, if we have like a smooth function, which is like defined on some open subset, and takes values in R. Such a function determines a parameterized surface. Where the idea is that we think of D essentially as like something two-dimensional, and then like this map shows as like how every point is moved to get something like curve here. So this point here is mapped up here, and like the value of how much it is moved up is given by this function f. So this point here is mapped to this point, and this point is mapped to this point. So the surface is of the form is just a graph of f. Which are all points in R3 where x and y are like from the definition of D, and the z coordinate is given by the function f of x. So that's the surface, and it has a natural parameterization or chart. There's a global chart which is given by just a function that maps x and y onto the point x, y, and f of x, y. So that's a well-defined chart. It's like defined on some open subset. So we have to verify that it satisfies like the properties. And essentially, the only somewhat non-tricky part is the non-degeneracy, which is like very simple and similar to this kind of problem, right? Like this map that I defined here is exactly of this form, where this one now is f of x and y. So the function here is just like taking one and then subtracting x squared and y squared. So the proof of the non-degeneracy is also exactly the same. Namely, I just take the x derivative of phi, which gives you like 1 here, and then we get like the x direction of derivative of f, and similar here we get like the y direction here. But they are never parallel because again, like the same argument as before, this one has a 1 here and this one has a 1 here, so they are never parallel, regardless of what the gradient is. So the same argument here as before, and then like it shows you that this one is indeed a parameterization or a Shang. Okay. So that's the first way to show that we have like a parameterized surface actually is by constructing it as a graph of some function. For example, that method doesn't apply to the whole of the sphere. It's not like a graph of a function because it's also not the parameterized. But what we know, for example, the sphere is like given by a constraint, right? We can say like the sphere are all points for which x squared plus y squared plus c squared equals to 1. So that's the sphere, right? Like a cutout but is constrained. And that's one of the ideas of the like the second method is like that you look at like things that cut out your surface in a nice way. And these things are called level sets. So in this case, again, every t defined on R3 is a smooth function. And then we fix a constant. And then we consider like the level set, and this one is the inverse image of the function under C, and this one has exactly this property that like the function g cuts out certain points. So in this example here, this one would be the function gx, y, and z, which is just taking the norm of the vector essentially. So that's the function g, and this one is the constant c equals 1. So that's an example. The sphere is cut out by this. So that's a nice statement, or like it's a nice construction. But like the problem is that that's not always the surface. For example, you can like think, give me a second about it, but like the cone, for example, where you have like the nice upper and lower part, that one is also cut out in a very similar way by a different function, but it's also cut out by some quadratic function. But this one is like has like clearly some kind of problem at this point here. Okay, it's like clearly something that's like a bit like singular. It's exactly like these functions that we looked at, like these curves, which we also didn't want to look at. Right? These points, like the cone looks like very similar to these non-regular curves that we have. And essentially, the same problem occurs here if you want to write down charts. You can't do that at that point because something breaks always. Because essentially, you go down one-dimensional or actually two-dimensional. The point is like zero-dimensional where everything else is like two-dimensional. Which is like similar here where you have a curve and then at that point you're for a second or so you're like zero-dimensional. And so this level set is not always a smooth surface, but there's a nice criteria for when it is. And that's the following proposition, which is S. It's a surface if we take like a gradient at some point, this one is the gradient of x, and this one is supposed to be never zero for all points which are being at the surface. And this requirement here that you only need to check it for the points of the surface is important. For example, if you look at the example of the sphere, the gradient is like the gradient G. You take the gradient of G, which is just like a quadratic thing. What you get is 2x in the first. Let's take the derivative with respect to x. Second, you take it with y, and you take it with c. You would say, of course, this one can be 0, right? It can be 0 at the point where x, y, and z is equals to 0. The point is, however, that x and y and z equals to 0 is not on the sphere. So that's like it's never zero. So that gives you a different way to prove that the sphere is like a smooth surface by showing that like you calculate the gradient that satisfies this property, and then the statement of the proposition tells you it's a surface. So that's like a really handy way to check that something is like a surface, and it's very powerful. So that's like, yeah, I think it's the most powerful method we talk about in a lecture to show that something is a surface. Okay. Before we go into the break, I would like to give you an idea of how to prove that proposition. So, the kind of the proof in pictures would be we have some surface, and what we have to do is we have to choose some point, which we call x0, y0, and 0. So that's a point on the surface, and what we have to construct is like a chart in a neighborhood. So we have to say like this point here, that something of that form needs to look like essentially just like a flat part. So it needs to look like very much like similar to just like this open subset. So like every point here, this needs to be deformed. So in every neighborhood of like the point, we have to find like something where it looks like just like a piece of R2. Right? That was the definition of the surface. So we have to essentially tell you how this like very curvy part gets like straightened out. So that's like in some way like what we have to do. So we choose some arbitrary point on the surface, and then at least one of the derivatives of G at that point is not zero. So that was like the assumption of, and without loss of generality, we can assume that it's just assume that it's the last coordinate. So we assume the last coordinate is not zero. Otherwise, we just like do the argument with one of the other coordinates. So that like essentially defines us like the c direction is like this direction, and x and y as being something in the plane down there. And now we use a very powerful theorem, which is namely the implicit function theorem. Can be solved. So we have this equation that defines our surface. We can always solve that for like the last coordinate. Once we have like x and y in C, which is like close enough to our given point. So that's implicit function theorem. It's like really important. If you don't know what this word means, then just look it up, please. So that's like, you should have seen that somewhere in your calculus course. That essentially says like, once you have such a condition that one of the coordinates is like not zero, and you have a function that defines, like you have an equation, then you can solve for this like variable. It's like also sometimes, or very closely related to the inverse function theorem. So we can solve for that, which means, more precisely, that means if we have it's a neighborhood which we call D of our point in our tour, and the function which we call f is defined on D and taking value in R, such that first of all we have that for every x and y in D, you get that if you plug these coordinates in, and for the z coordinate you use f of x. So that's now a function. That's now only a function of depending on x and y, but this function is always constant, is equals to the constant that we choose. And moreover, all points on the surface in some neighborhood O of x0, y0, z0 is of this form. So we can solve like this equation for C, namely there exists like a function that tells you, given x and y, what is the coordinates. So in this picture up here, this one is like the function that tells you how this point is moved. It's like the blue part is essentially it. You have a point, let's say you have a point here, it would be x and y. Then this one here is given by x and y and f of x and y. So this point, like just like the f gives you the z coordinate of that point. So it like tells you how to reach that point, like the z coordinate of that point. But of course, once we have that our surface is like locally described as like in this way, we see that it's nothing else than what we described earlier as the graph of the function, right? So that's nothing else than saying that f, like the surface is locally the same thing as the graph of the function, right? So we can use the same trick substitute as before. can define now the chart, which is defined on D, and takes value in R3. And it says that just this functional. And the same argument as before says that this one is a coordinate. So we found now at any point, like there's x0, y0, and was like arbitrarily chosen. So on any point we found now a coordinate chart which describes the surface in that area. So that means like that's exactly what we had to prove, right? We had to find like a coordinate chart around each point. So that's the proof of this proposition, is that once we know that this one is not 0, then we know that we have a surface. So and I think that's all I wanted to tell you about like the general concepts of surfaces. Yeah, so it's like this part is really like the most universal one, or the strongest ones of the theorems that I will tell you how to construct or how to show that like a certain object is a surface. So then that's quite useful. Okay, now we go in a break of 15 minutes. So 2 minutes after 30 we start, and then we talk a little bit about the calculus on surfaces, about like tangent vectors and other interesting parts. So.
With the terms, parameterize the surface from the open set to the R3, and the surface is something like some manifold.
Yeah, so like so like parameterized surface is like just like some open subset, which is like the form somewhere. And like the surface in general can be like something where you have like local but like not local. Just like so if you know like submanifolds, it's like most of them are like submanifolds.
I know. And I don't know how to prove the quantities of the surface. If I know you.
No, it's not like yes. So it's like,
I don't know the proof.
it's usually harder to do like it's usually like pretty hard to show that something is not a surface. Like there in this case, what you can is like you just assume that you have some chart, and then you have like certain curves, right? Like the ones that like go forward, and you look at like what happens with the changing vectors. That's something that I talk about how changes work. But essentially, it's like what happens with the curves, and then you see that like they always get like contracted to a and that means like you lose in some way, like this condition that You have to say like, okay, I choose some chart, and then I look at certain curves, like I give you the root and I end up like curves like this and things like that. And that visualizes at that point, I always have like something guys have a problem? That's like in point in the flat space. And like with this here, it's relatively simple. The upper half here, and then you just project down. Like point, like that up here, say like this point, it's just like we project it down. That's where it's like projecting down is like or you say like every point down.
所以说一个球，它的这个意义上不是一个 parameterized surface，因为我没有办法用两个东西 parameterize，而是一个开始，没有办法来 parameterize，但是我们可以用两个 class 在上面设两个，然后去做一个 class，下面做一个 class，然后使得它这个被覆盖到。所以说，一个点它可以
You get like essentially every point on the cone, you can protect down in some way like you go. But the problem is that like this point here is protected. At this point, we have like two protections. And you don't know that you protect it down there, or you protect it down. So like really that's like how design way to protect this two because it has to be continuous. Because nearby points which are like clearly would be protected.
你要必须要有一个负点意义，比如我设在设这样偏 Z 对不对？可以设偏 G 偏 F Z， 然后这个我这个 X Y F Z 的，然后就可以写那个第一个条这个 graph， graph 就是 X Y G X Y， 然后这的话就是 X Y F， 就是对应导出来一个词。
And that's according to that proposition, I think the code is
but it's like if you do exactly that, like what you change is like this, right?
其实中心就做一个平移就好，但是无所谓，这个东西我觉得在这画这个天。
If you do that, then like you get a minus. But the problem is that at x, y, if you put all of them equal to 0, then this guy vanishes, right? X, y, everything is equal to 0. So this one is actually 0. So we can't use that because like here I require that it's not.
Oh, for sphere, it just is defined.
Yeah, because here we have like, and you always have this property that you have to check it for all points on what is cut out. But the nice part about the sphere is that like the sphere, this one never vanishes. But at the vertex, exactly at the vertex, this guy vanishes. The vertex is part of the solution. That's the problem. What is so that's the problem.
So if it is x1, it is.
Yeah, like if you put a plus here, then it's like this here. But if you have the minus sign, it's because like clearly x, y, like the 0 point is part of the code. So that's like the difference.
你说明对这个我觉得这个这个事情，你单元需要来配置。
Yeah, so I would like. Let's continue. I would like to continue, like discuss a bit more with you, but maybe we do that afterwards, after the class. For now, we have to learn a little bit more about calculus. Okay, so we would like to talk about now about calculus of on a surface. So you have like this round object, and what you, for example, would like to describe now, if you have like a function living on the cylinder, how that changes if you go like from this point to this point. You have a certain function defined on that surface. How is it like changing? What are the values? And like, can you make sense, for example, of like infinitesimal changes, and then you take derivatives and things like that. So that's like what I mean with calculus. And if you like one difference is like that, like on like an object like this, you have like different coordinates or like different directions where things like get interesting, right? Like you have to say like in some way you have to say like specify a direction first before I can tell like that something changes, right? Like I mean, for example, it's very hard to visualize like a function on it. But for example, if I say like, yeah, like if I want to say like the color, how that changes on the cylinder. So if I have like, then of course I can have to specify a direction. If I say like in this direction, for example, nothing changes. But if I cross it here in this direction, then at some point the color changes. If I'm at that point, so I have to specify a direction on the surface before I can even talk about that things change. I have to say like in which direction do things change. And that's what is given, like this direction is called a tangent vector. So that will be the first part that we talk about, is like tangent vectors which give you directions. And then the second part is like how do you measure, like in some way, changes of a function in this direction, and how to intrinsically measure, for example, how long a vector is. So that will be the second part, but I'm not sure if I have time for the second part. And the principle is essentially is like the following that we follow. We define a property on the surface in terms of the coordinate charts. So whatever property we would like to discuss on the surface, we try to formulate that in terms of the coordinate charts, because that's, in some way, that's the only thing that we know about the surface. It's like some abstract set, some abstract subset of R3, but the nice part about this abstract subset is that it has charts around every point, so that we have to use in our definitions. And an example of that is like when we talk about what a smooth function is on the surface. So a function which is like a function defined on the surface. So this one is our surface. See, it takes values in some r to the power k. And this one is called smooth. If all compositions the form of coordinate charts are smooth. So the picture here is the following. We have our curved surface, and we have a function that says like, that maps certain points of the surface into R. So that's the, and we would like to see when that one is smooth. So when we say like, that for example, like the color on the bottle is not smooth, right? Like it changes like very abruptly, like there's some discontinuity here. Like on this one it's silver and here it's white. So that's like very, like a strong change. But we would like to say that it changes very smoothly. But like we don't know like how to define things on the surface, right? There's like, we don't know what it means to take derivatives or stuff like that, of that function. It's like some really abstract thing, like on the sphere. How do you take derivatives of functions that live on the sphere? And the idea is, we look at like parameterizations or coordinate charts as part of it. So this one maps then to our surface. So we get like a nice subset there. And then we say that this composition, which now is like a really nice function because it's like a function from R2 or some open subset of R2 into Rk. And that one is like very easy, or like that we know how to say that such a map is smooth. So that's the idea. It's like we would like to say this one is smooth. But that's hard to say because we don't know what is like smoothness on the surface, and the way we say it is we pull it back, or we take it back to something that we know, and that's like smoothness of functions between open subsets of R to a power. So that's the idea. It's like that we require all of the compositions to be nice and smooth. So in practice, that means that like, if you have a surface that you might have to work a bit hard. For example, we had like the sphere. There were like 6 charts. So if I give you like a function that is defined on the sphere, you have to look at like each of the coordinate functions in each of the charts, and then verify that all of them are like all of the 6 expressions are like smooth. So that might be a bit involved, but it's yeah, like that's the best you can do. These compositions, they have a name. These ones write it down. Called the component coordinate expression. We have a function and we can express that in terms of this other coordinate, and then by just taking the composition. So that's like and an example would be, for example, we can look at the map which is x, y, and z equals to z on the sphere. So we have the sphere that we had. And then what we need to do is like we can, for example, take again the same map that we looked at before, where this one was mapped to x, y. That was our chart. So what we have to do is like we have to pre-compose that with F. So what we have to look at is like this composition, where we first go to the map phi, and then plug that in F. So this one is nothing else than plugging in phi first in F. So we do that. So it's F of x, y, 1 minus x squared equals, and then now this function f is defined by this c component, so this just gives us and this one turns out to be smooth. You can check that by taking the derivatives and stuff. And now you have to check that like for all of the different over charts that I described before, where you cut out like a different part, and then you end up with like also like a slightly different function, and you have to check that it's also smooth. Checking. And there's a nice result, which I don't want to go like too much into detail, is that, for example, on the sphere, we saw that there are different kind of coordinate systems, right? Like that you have like the coordinate systems of like polar coordinates and the systems that like these kind of coordinates here. And the nice part about like this concept of smoothness is that it doesn't depend on which chart I can choose, as long as the charts in itself are like compatible. But I will not talk about this compatibility like too much. But it's like something like for the people that are a bit more mathematically oriented, they might be like, the natural question is like, okay, now this depends on all compositions, so that's usually very hard to check. Do I have to really check it for all, or like is there like dependent on which kind of charts I choose or not? So that's like answered by this statement. It's if the charts in itself are compatible, namely that like certain kind of maps are smooth, then it doesn't matter which chart you choose. So it's, but I don't want to get like too much into detail for this course. So that defines you the concept, like this one, defines you the concept of a function that is smooth on the surface. But it's usually more like simple to talk about or like to study a surface by looking at like things that like map into the surface. So for example, we could like look at like curves in the surface, which usually describe a little bit more like the geometry of the surface than a function that is defined on the surface. Like in mathematics, there's like essentially two ways to study objects. It's like either we define objects that live on the thing that we want to study, so like smooth functions that live on the surface, and we like derive certain properties from that, or we look at like things that map into the surface. So these are like